Hi there, my name is Sydney Thomason. I'm a graduate student here at LSU Online, and today I'm going to be talking about run-of-river hydropower. So to get started, just kind of want to do a brief introduction on hydropower and run-of-river. So hydropower is a renewable energy that uses flowing water to generate electricity. There are three main types of hydropower. Those are impoundment, pump storage, and diversion. Impoundment are dams, which is the most common form of hydropower, and diversion is run-of-river, which I will be talking about today. In 2026, hydropower generated approximately 26% of the total U.S. utility scale renewable electricity and approximately 6% of the total U.S. utility scale electricity. Hydropower plants are relatively low cost when it comes to construction, operation, and maintenance. Most hydropower plants cost are site specific, excuse me, and so cities and states are able to better control the cost. I am so sorry if you can hear my cat in the background. Moving on, uh, onto just run-of-river hydropower background introduction. So, like I mentioned, run-of-river is a diversion type of hydropower. It uses a natural decline slope of a river that has the water flowing down. Some of that water is then diverted and guided through a channel towards the penstock, where after traveling through the penstock, it spins a turbine and generates electricity using a generator. That water is then returned back into the river downstream. So for run-of-river, dams are not necessary because there is no need to create a reservoir for that water. So the capacity of the power plant is dependent on whether the river is flowing or not. And typically for run-of-river hydropower, there's a capacity of 40 to 80%. So the process of it, there are essential components to a run-of-river hydropower plant. So in order for it to operate, there needs to be a significant flow of water within the river, and the river needs to have a significant hydrostatic head. So to actually determine the flow of the river, it's ideal that data is taken daily and seasonally to determine if the fluctuation would allow for a efficient plant to be installed. The penstock of the plant carries the water down to the turbine. And so in order to have a properly functioning plant, you need the correct diameter and wall thickness of this said penstock, and that will be different by plant. Nominal flow is also necessary, which is the max flow rate that can move through the penstock and the turbine and doesn't result in any energy losses. The turbine is also another key component and needs to be selected specifically for the plant being installed. Turbines can be impulse or reaction. Impulse turbines are better for sites with a high hydrostatic head, whereas reaction turbines are better for those with a lower hydrostatic head and a higher flow. Lastly, the generator is another essential component, obviously. And so the generator is located inside the powerhouse along with the turbine. And this is what actually converts the energy from the moving water into usable electrical energy. So how it works, just kind of a schematic overview. So water upstream will be diverted down the penstock or sometimes through a channel first and then the penstock, but eventually through the penstock, which is when it will reach the powerhouse, which houses the turbine as well as the generator. And so the generator inside, like I said, converts that energy into electrical energy, and then that is transmitted across power lines to respected areas. And like I said, once again, that water from the powerhouse is then returned downstream of the river. So the energy output is going to be dependent on the geographical features of the plant and will vary from site to site. To determine if the plant is suitable where it is going to be located, the power is calculated using the equation shown on this slide, with Q being the flow of the water in cubic meter per second, and H is the hydrostatic head in meters. The energy produced by run-of-river plants, like I said, will vary seasonally as the flow of water will increase or decrease. One study found that in the alpine geography, the production increased in the winter about 4 to 9% and actually decreased in the summer by 2 to 22%. Certain places like Canada classified their plants by their generating capacity. And so Canada, for instance, has four different categories: micro, which is less than 100 kilowatts; mini, which is 10 kilowatts to 1 megawatt; small, which is 2 megawatts to 50 megawatts. And then they say anything over 50 megawatts is a run-of-river hydroelectric. Some plants have been known to have large capacities, but this is typically the range for most run-of-river hydropower plants. So the cost of run-of-river hydropower plants comes primarily from the construction and installation. The turbine makes up most of the cost, but when calculating the cost of these plants, all aspects are taken into consideration. One study actually found that the design, tools, surveys, and assessments, as well as other indirect costs, contributed about 13% of the total cost. But like I mentioned earlier, once in use, the maintenance is relatively low cost. Um, in Canada, the average cost, sorry, my cat just jumped up on here. The average cost in relation to the energy output in 2008 was $2,000 to $5,000 per kilowatt. So the customer was paying 4 to 10 cents per kilowatt hour. In rural regions, the cost can be a little bit higher. Um, it was found in 2008 that the customers in rural regions paid 12 cents per kilowatt hour, but the overall cost will fluctuate depending on the flow of the water, how much electricity is actually being produced, where it is located, things of that nature. But it was found that run-of-river electricity, the cost of it was higher than hydroelectric dams, but lower than electricity produced from sources like fossil fuels, and that data was taken from fossil fuels in Oregon and California. All right, now moving on to plants, starting just with some current plants that are already installed and in use. So countries with existing large hydrostatic power are also becoming leaders in these run-of-river plants. So these countries include China, Brazil, and Canada, with China having over half of the world's run-of-river capacity. Canada's run-of-river industry contributes about $150 million to their GDP each year, mainly in their production components that come from run-of-river plants and like turbines, generators, things of that nature, which are then exported, contribute to a lot of their GDP. And these complexes, the run-of-river plants that actually contribute, are mainly found in Manitoba and Quebec. Other areas like Nepal, Norway, and Switzerland and Austria are starting to grow in run-of-river plants due to their big resource of being in a mountainous area and having the rivers that flow downstream. So some future plants, just to talk about quickly. So remote areas are starting to have higher benefits of run-of-river plants, as they allow for a local energy source that doesn't require the installation of these like big, massive transmission lines to move this energy around. So to install common transmission lines in remote communities would cost a significant amount of money and produce additional greenhouse gases localized in that area. Small run-of-river plants would provide remote communities with a source of energy that would likely be enough to power their kind of everyday needs for a relatively low cost. Certain communities and certain areas have already tapped into this energy, specifically areas in like First Nations in British Columbia, as well as Kenya, are starting to see the potential benefits of these run-of-river plants. Additionally, in a study that was conducted, they found that Peru has 11,965 suitable sites for the installation of run-of-river plants. 5,862 of those sites have a capacity of 1 to 20 megawatts, while 6,103 sites have a capacity of 0.1 to 1 megawatts. However, it was also found that the rivers in Peru we're not yet fully developed to handle this generation that is needed, and that the number of sites decreased as the river order itself increased. So there was still some constraints to the amount of future plants that could be developed, but there is potential for Peru to really start to grow in this area. All right, so moving on to advantages that come with run-of-river hydropower. So in many places, the sustainability of run-of-river plants has grown in importance, and many places require studies to actually be conducted before these new plants are built, and they look at various factors like social, environmental, and economic. So there is a lot of emphasis and pre-data that is done when building these plants. One sustainable factor of run-of-river plants is that there's typically always a supply of water present to power this plant. The flow rate and the amount of water may vary, but there is usually always that supply of water. Run-of-river plants also have a high lifespan, with them lasting typically over 50 years. Since run-of-river plants are renewable sources of energy and they work off the flow of water, they don't burn fossil fuels, which means they don't emit greenhouse gases, which is a good plus. The lack of greenhouse gas emissions is a significant advantage to these plants, since there is a large concern with the amount that is already being put into the atmosphere and kind of how much more it can handle. So the environmental impacts, like I mentioned, they do not emit greenhouse gases. They also don't require damming of a river, which can lead to flooding and changes in the actual river form, which then will influence the ecosystem. So you don't have to worry about any of the consequences that come with putting up a dam. Unlike dams, run-of-river plants can still allow for the migration and movement of fish downstream in the river. When proper screening and or fish passes are in place of these plants, that keeps the fish from being accidentally drawn down to the penstock and into the turbine. But with the implementation of screening and passes such as fish ladders, fish can still migrate and move within the river itself. And so in this picture here, this is actually a fish ladder in a run-of-river plant. So how the fish can keep migrate and moving downstream. So the cost already mentioned a few times, they are low cost. They have a long lifespan, so there's not really new costs that are associated with it unless, like, it was to get damaged and needs repairs. The transmission lines of run-of-river plants can be connected to local energy grid of an area, which leads to minimal energy loss because there's not as much transportation happening. Additionally, some governments are providing incentives for the installation of run-of-river plants due to their green nature, aka their lack of greenhouse gas emissions, and the fact that they are a renewable energy source, and that some governments are wanting to transition more to that. All right, just like there are advantages, there are always disadvantages to things. So the sustainability disadvantages, one key factor influencing the sustainability and effectiveness of run-of-river plants is the site where they are located, since they do require a river with a significant flow of water. It is not ideal to put a plant on a river that is likely to dry up, because there will be some of that diverted water will kind of cause a gap in the river of a lower flow. Additionally, the size of the plant is dependent on the size of the river. So if you were to try to put a large plant on a small river, that would not turn out very well. Run-of-river plants do raise environmental concerns due to their impact on downstream movements of materials, as well as their midstream water depletion, which I kind of mentioned just briefly earlier. These impacts, as well as others, can be viewed as sustainability concerns and factors. But like I mentioned, especially with migrating fish, there are some practices that can be put into place to help mitigate that problem. Since the energy production is dependent on the flow of water, depending on the seasonal variation, the run-of-river might not always be a sustainable high energy source or electrical production, because it will vary. It won't always be constant. The disadvantages of the environmental impact. So they require this diversion of water upstream in order to flow the water through the turbine, which can cause a disruption to the natural flow of the river itself, which could then result in a hindrance in the downstream movement of nutrients, sediments, species, and more. This could then change the actual biota of the stream. Additionally, if the flow of the river is not studied prior to construction, the habitat itself could be altered due to excess depletion of water compared to what is normal depletion of water for that river. The space between the upstream diversion and the downstream return of water is where most water depletion happens because you're not getting as much constant flow right there. And this could prevent or hinder fish migration, reduce habitat space to the amount of water that is left in that area, which could then increase competition between organisms there for food and for resources and alter the vegetation itself. The construction of the plant can also cause environmental impacts due to the creation of new roads, which would lead to erosion of the riverbeds, as well as the installation of the transmission lines in the area. Although more prevention methods have been introduced to help mitigate all of these problems, if a run-of-river plant lacks a proper screening or fish pass, these migrating fish that use this river could find themselves drawn into the penstock and into the plant and into the turbine, which is kind of one of the big environmental concerns associated with run-of-river plants. The cost disadvantages. So run-of-river projects and plants require initial studies and surveys as well as permits, which can be a little bit bigger costs on top of the already installation costs. Since run-of-river plants do not generate as much energy as traditional energy sources, there is kind of this larger payback period for the plant in response to what is generated. Site locations for run-of-river plants could potentially cause displacement for those living with the area. Resettlement and rehabilitation costs are potential to arise if a community, for some reason, is needed to be moved from the river due to the installation of the plant. As it was shown back a while ago in the cost side, the cost of electricity produced per kilowatt hour may be more expensive than other forms of renewable energy sources. Like as I mentioned, in 2008 in Canada, the cost per kilowatt hour for run-of-river electricity was higher than that of hydroelectric dams, but once again was lower than electricity sources that originate from fossil fuels. So there is some kind of falls sometimes middle ground in the cost of electricity produced. So just kind of reviewing everything we've talked about in this presentation. So run-of-rivers use a natural slope of a riverbed and they do not require a dam. So the typical disadvantages, impacts that are associated with a dam are not applicable when it comes to run-of-river. The diverted water from upstream flows through a penstock and moves to a turbine, and then through the generator, which transforms that flow of water kinetic energy into usable energy and electricity afterwards. And then that water that passes through is returned downstream in the river. The energy output can be anywhere from less than 100 kilowatts to over 50 megawatts, and the capacity factor is 40 to 80%. The key components and essential components that you need for a run-of-river plant are obviously the river, of course, that is suitable for the plant size. You also need the penstock, the nominal flow, the turbine, and the generator to have effective and well-running plant. The pros, just to give a quick, I know we just went over them, but just debrief over them. The pros, they have a high lifespan of typically over 50 years. They do not emit greenhouse gases, which I think is a really big pro and advantage that comes with run-of-river hydropower. if properly installed and built, they can still allow for migration of fish, which is, I know, a really big concern. And so when those are properly in place, it kind of helps mitigate that and adds more pros to it. And then also the generated electricity can be transmitted locally with implementation incentives offered. The cons, you are really dependent on the site, the river size, and the flow for how well these plants will work, especially in their given area. They can alter river habitats and ecosystems, which can play bigger roles down the line as the world continues to change and evolve. If there is improper screening or there's no fish pass installed at all, it can start to really harm these fish species as they are drawn into that penstock and down the turbine, especially for, I know, migrating salmon is a big concern for many areas that are starting to implement these plans, specifically in Canada. And then also the payback period can be longer because you may have some higher costs at the start of the whole project, and it may take a while for that payback to start to build up since um, the cost of it is not like it, there's not quite as much like income associated with these electricity that is produced. So sorry, got really tongue-tied there. So just some closing thoughts. It has its share of pros and cons, just like any sort of energy source will, with the pros primarily, like I've mentioned multiple times, the lack of greenhouse gas emissions, which I think is just such a big concern that it's really highlighted here, whereas the cons are primarily with some of the environmental impacts that can happen and just the limited site availability. They are located all over, primarily in China, Brazil, Canada, and also mountainous regions like Nepal, Norway, Austria, and Switzerland. They can be highly beneficial in remote communities and might serve them better than some of the traditional sources of energy just due to availability and the fact that they are not as expensive to implement. But like with any sort of energy source, really anything at all, more research should always be done to really get a holistic view of these plants. And I believe a good place to look for more research would be potentially looking into the addition of these plants on artificial rivers that are sometimes located within cities and seeing if they can still work the same there as they would on a natural river slope. So here are my references for this project and this presentation. Thank you so much for listening to me talk about run-of-river hydropower. I hope you maybe learned something new. I know I really did throughout this whole project and time of looking into all this. So thank you for your time.